So this video is to give an overview of NMR spectroscopy, particularly the nuances associated with proton NMR. But let's recall where you guys began your NMR adventure with C13 NMR. So with C13 NMR, what we're focused on is mainly thinking about the number of peaks in each spectrum and the chemical shifts were the two major factors that we had to interpret here in order to associate this with individual chemical structure. We also showed how relative peak intensity can provide some useful information in that the peak intensities of carbons that had no hydrogens were greatly reduced compared to those that had more hydrogens. For example, this signal up here, which you would probably identify as a carbonyl, has no hydrogen atoms attached to it, which is why it is so much less intense than the other three signals in this C13 spectrum. Proton NMR contains the same number of same other characteristics in addition to a few others. So we're also concerned ourselves with the number of peaks, which relates to ideas of symmetry and connectivity within the molecule. And we also interpret chemical shifts, which tells us what the environment is of each hydrogen atom that we're observing. But here we're also concerning ourselves with two other pieces of information. Integration ratios, which tells us how much of each hydrogen atom there is. So integrations are how we can quantitate hydrogens within a molecule. And we're also concerned with this idea of multiplicity, which indicates how many neighboring hydrogen atoms are on an adjacent atom. So here with this idea of multiplicity or signal splitting here, we can get a lot of powerful information to interpret proton NMR and get a very specific structure. So in determining the number of hydrogen signals, we need to think about topicity, which is how these different things relate to one another. And it's very much related to the idea of stereochemistry. So based off of connectivity, we should be able to see whether or not things are homotopic or enantiotopic to one another. So this should be something that you're very familiar with based off the rest of your organic chemistry experience. But it really, for each of these types of systems, they're both chemically equivalent. So we cannot see them as different on the NMR experiment either. And so a simple replacement by deuterium shows that we could then superimpose these two systems on one another, and we would not see any difference. Even in the case with enantiomers, we don't see any different NMR behavior. So even while these two compounds, the deuterium replacement test produces a pair of enantiomers, they still have the same NMR properties associated with them. So the chemical shift associated with each of these hydrogen atoms would be the same. The situation gets a little bit more complicated when we have distereotopic related protons to one another. So in the case of this molecule here that already has a stereocenter, the adjacent CH2 signals would actually have different NMR signals associated with them. So when we have a stereocenter within a molecule, things can get a little bit more complicated, but we'll probably not see too many examples associated with this types of things. But each of these hydrogen atoms would be in a slightly different chemical environment than each other, and they would have a different chemical shift and be non-equivalent. Chemical shift is also very powerful and useful information for us to look at, and it's related to really how we can determine what functional groups are present in a similar way to FTIR. So it's an analogous complementary technique to that. And it's really based off of, again, the electronegativity of nearby atoms changing the electron density, which impacts the applied magnetic field to those individual hydrogen atoms here. So located on the slide here, we have a number of different chemical shift ranges. It's good to have an idea between where many of the sp3 systems come. The sp system sneaks into the middle of this, as well as many of the sp2 hybridized carbon-hydrogen based systems as well. And so there's kind of a clear delineation between these, or right around 5 ppm. And then we have these carbonyl containing functionalities as well. These are just good ranges to keep in your mind so that you can begin thinking about what types of structures are related to these types of systems. Now, whenever you have a proton that's attached to a heteroatom, such as a nitrogen or oxygen, you get much wider possibilities in terms of the chemical shift ranges associated with that. And that's seen a little bit with this carboxylic acid peak here. But alcohols, phenols, amines can all really appear in a number of different places across this NMR spectrum regime here. And they tend to overlap with what we think of for typical carbon-hydrogen signals as well. Most of the time, these signals are broad, though, and so they're readily identifiable by that type of a characteristic, although not always, and some of them can show coupling under the right conditions. So integration. Integration is one of the newer parts associated with this NMR technique compared to carbon, and it's a very powerful tool for us to keep in mind about what's happening with our data set. So the integration represents the area underneath the peak associated with each of these NMR signals, and it provides us a relative ratio within a molecule of the hydrogens to one another. And so as you can see here, we have our lowest integral set as 1, and then we have other integrals that are approximately 1.5. This other one is approximately 1, and this one here is 1.5. Now, we can't have 1.5 hydrogens on an individual carbon atom. Carbon has to have 4 bonds to satisfy it. We can't magically have a hydrogen in half. And so what we have to do is we have to adjust this to our actual values. So what we'll often do is we'll find a multiple that we need to multiply all of the numbers by to give our actual values for our integrals here. So if we multiply each of these values by 2, we can see that we get closer to whole numbers that make sense. So here we would have this one go up to 2, this one become approximately 3, 2, and 3, associated with numbers that make sense for groups that we should be seeing in hydrocarbon-based species. CH2 groups, CH3 groups, CH2, CH3. Multiplicity gives us a lot of structural connectivity information. And so it represents the number of hydrogen atoms on the adjacent carbon. All right, so our integral values tell us the number of hydrogens on the signal that we're looking at here. For example, this orange highlighted peak here represents this CH peak on this CHCl2 carbon. And it is a triplet because it has 2 hydrogens on the adjacent carbon atom, which splits it into n+1 number of peaks. And so we begin seeing a signal associated with each of these. And so for HA, we have 1 adjacent proton on that carbon atom, and it splits it into a nice clean doublet. All right. The ratios of these peaks are determined by Pascal's triangle, and they fall out fairly regularly, although there is minor distortion. As you can see here, this is a little bit of a lean. They're not exactly 1-to-1, but it's close enough for us to call this a simple doublet. So again, the presence of this splitting for HA is due to the fact that the neighboring carbon atom has 1 hydrogen, which splits the local magnetic field into two different changes of energy here, which gives us rise to this doublet pattern. So again, what's happening here is that we have HB acting as a tiny bar magnet in itself, and that gives us 2 orientations that it could be adopting when we excite HA. And so HA feels a little bit of additive effect when HB is aligned with the magnetic field. And then it feels a little bit of a decrease of the external magnetic field when an HB is aligned against it. And this ends up producing these 2 different energy patterns, and hence a doublet signal associated with that. There are more possible states as we increase the number of neighboring carbon or neighboring hydrogens on the adjacent carbon atom, and so we can get more possibilities associated with this. But you can see the middle here grows fairly rapidly because there's more combinations of these states that are degenerate or the same as one another. And so this typical quartet pattern, which appears when you have 3 neighboring hydrogens on the adjacent carbon atom, falls in this 1 to 3 to 3 to 1 pattern. And so, this is basically called the spin-spin splitting, or this J coupling value, and this is through bond effect of these hydrogens communicating with one another, using the electrons to kind of relay this information back and forth. All of these values fall out in this nice intensity Pascal's triangle type of relationship, and you should know how to name each of these associated patterns associated with it, which have fairly common names. And they're all following, again, this n+1 rule. There's a number of different structural motifs associated with this. One of the things to be careful about is that you can see here the intensities of the internal signals grow fairly quickly compared to the external ones. And so sometimes if you have a known net, it can be very hard to pick up that one intensity when the inner line is 70 times more intense than the others. But in general, this allows us to put together our structures and have connectivities of these molecules work out in a way that allows us to unambiguously assign a structure. So a couple of things that you should keep in mind with multiplicity. When protons are equivalent, they cannot couple one another. And so in this molecule here, which is symmetric, and these hydrogens are the same as those hydrogens, no coupling is observed because they're the same hydrogen species. In general, what we see is that for sp3 hybridized systems, in general, what we see is that we can only have splitting when things are vicinal or on adjacent carbon atoms. Once the hydrogens are multiple carbons away, the coupling values are so small that we can't pick it up on our system here, so we typically do not see those types of systems. And the n+1 rule really falls into effect when we have all of the adjacent carbon hydrogen atoms being the same. That is, they're either the same in terms of hybridization, but more generally, they're equivalent in terms of their NMR behavior. So there is a specific measure associated with the separation of these lines. We're not going to focus too much on it in this part of the course, but we will in second semester. And this J value is a separation that we can measure between the peaks. It's measured and reported in Hertz because it's actually constant, because it's part of the molecule and it's not affected by the magnet. And so what we'll see here is that for most alkane type species, this is on the order of 7 to 9 Hertz, and it tends to be fairly standard for this type of system. Now, when we have sp and sp2 hybridized carbon hydrogen-based systems, it can get a little bit more complicated, but that's something that we're going to save for second semester here. So one of the things to realize is that if hydrogen A couples hydrogen B, this splitting will be the same in each pattern. So the distance of JAB here will be the same as the distance of JBA. So whenever we measure these, we can often match these up if we have very slightly different values between the individual signals. So as I mentioned, there are situations where JAB does not equal a secondary coupling constant that can be applied here. So when this happens in a situation like we have on the right here, we can get what we refer to as patterns that don't fit Pascal's triangle. All right, so there are ways and rules for interpreting these types of more complicated multiplets, but we're not going to focus on those in this first semester part of the course. But should you come across something like this, you should know that it's a situation that likely involves sp2 or sp types of systems, and we're going to deal with more of this in the second semester part of the lab. So most of our systems will fall into this nice Pascal's triangle here, where you should be familiar with the relative intensities of each of these patterns, and we can name those. There are additional complications that can arise in signals when the J values are of a very similar size and the peaks are not resolved, and they're actually very similar chemical shifts of the two coupled species. And so what happens here is you get non-first order behavior, so things do not follow Pascal's triangle, and this is an example of one of the resonances of hexane, where all of the chemical signals are coupled to one another from a lot of the CH2 groups there, and they're both coupled to one another, and they're similar chemical shift values, which causes this distortion of the pattern from our typical Pascal's triangle rules associated with multiplets. For these types of systems, you do not have to interpret those in terms of the coupling tree, but what you should do is just report a range here, and we can label it as a multiplet. So let's look at a good way of thinking about NMR data sets in terms of proton NMR. There's a lot of data here for you to keep track of and systematically organize. And that's really the major key with being successful with proton NMR, is keeping track of all of this information. So what we're going to have you guys do is draw partial structure tables. This allows you to organize your data sets up and make sure that you're not leaving out any part of your analysis in your work. So the first part here is you're going to want to start off by looking at the total number of resonances, okay? So for example, in our example spectra shown here, we have this particular molecular formula here. It would be useful to calculate a du associated with this, but mainly we want to know how big of a table we should create. So we have 5 total resonances, so we're going to need to create a table shown here in our step 2 that has the ability to accommodate those 5 resonances. The next thing we're going to do is we're going to correct the integrals here. So we want to make sure that the integrals represent whole sum numbers associated with these. And so we can correct each of these by multiplying them by 2. Then what we're going to do is we're going to begin filling out the table with the information that we have. So we're going to start with the chemical shift associated with each NMR signal here. And so for systems where we have an even number of peaks, we're going to try to predict guess what the center of the resonance is here. So that can be done by just taking an average of these two numbers here and to get our correct value of 4.13. And then we fill in this information accordingly associated with each of these signals. All right. So here we would have our salsa quartet, and we would fill in the integral values as well. We then use this information to think about what possible partial structures we have. So this is the part where we're interpreting the values that we've templated into our data set. So the first thing to think about is the integration values. So for the integrals here, we can think about we have 2 hydrogens associated with this, so it's most likely that we have a CH2 group that we're talking about and that we're observing with this individual signal. And then we have our partial structures. So we have 2 possibilities for this partial structure. We could have a partial structure here where we have a CH2 group adjacent to a CH3 group, which would give our quartet that we've observed with this signal. Or we could have one where we have a CH2 group next to a CH2 group, and on the other side, a CH group. All right. So to narrow down these 2 possibilities, we then interpret our remaining piece of information that we haven't analyzed yet, and that is our chemical shift information. So in this, we would say, well, this chemical shift is around 4, which is pretty high for most CH2 groups that are sp3 hybridized. And so it's likely that this is attached to an electronegative atom like an oxygen. And if that's the case, we really can't have this type of a system here, because there would be no electronegative atoms to change the chemical shift of that CH2 group. So it's most likely that our partial structure is this particular signal here. And so we would systematically go through this, coming up with partial structures that fit the information associated with each of these signals. Again, starting with the integrals to determine the signal that we're taking a look at, and then looking at the adjacent signals that are associated with each of these ones. Okay? It's a good rule of line to underline the coupling partners and circle the portions of the molecule that we're looking at. And if we keep this convention down, it'll allow you to make sure that we're keeping all of these things fairly straightforward. So in this analysis here, what we're doing is we're beginning to see partial structures that we can begin to overlap to create a larger structure. All right, so we could say, well, it looks like this partial structure here could overlap with this partial structure here, because this CH3 group could be this CH3 group that we're inferring its existence through this green underline associated with this. And this CH2 group here that we're inferring could be the same CH2 group that we see there. And so we could combine these two into a single partial structure of O, CH2, CH3. And then if we look at the other particular systems that we have here, we could combine this one and this one, because this CH3 group would be the same as that one, and then combine these two together as well, and we would end up with a partial structure that looks something like this. And we can see that what we have remaining here are two bonds that need to be connected together, and we would end up with our final structure associated with this individual molecule. So let's take a look at another example here, and let's go through how we would think about partial structures and determining the particular structure associated with this just from the proton NMR data. All right. So again, what I'm going to do is I'm going to look at the number of signals that I have here. Well, I have one signal here, two, and then three. And then I'm going to start writing out the chemical shifts associated with this. And so here I have a chemical shift around 4.235, we'll say. That's probably more sig figs than we need. The integration value is 2 hydrogens. And then when I look at this signal here, I see a 1 to 3 to 3 to 1 pattern here. It has 4 lines, so I'm going to call that a quartet. All right. My next signal here has its center at 1.21 parts per million. And it integrates for a value of 3, so it's 3 hydrogens here. And it is in a 1 to 2 to 1 intensity region, so it is a triplet. And then the final value that I have here is at 1.1. We don't see a blow up of this, and it looks to be a single peak as indicated by this peak picking value here. And this value here is close to 9 hydrogens. All right, so this is going to be a singlet. All right, so I've filled in my part structure table here. We're going to start interpreting that in a sec. But let's go back and let's calculate our du here and take a look at this molecular formula. And so if I do my du value here, I have 2 times 7 plus 2. And so I could have a total of 16 hydrogens given that I have 7 carbons. And what I really have is 14 hydrogens. And so I'm missing 2 hydrogens here, which if I divide that by 2, gives me my du of 1. And so I have 1 double bond, or 1 ring, in this structure. So let's go back and take a look at what my partial structures can be to fit for this NMR data. So let's take a look at our quartet here. To have this here, we're again looking at 2 hydrogens associated with the integral value. And so we have a CH2 group, which is what we are observing. And then we're going to interpret the multiplicity. So to figure out the adjacent carbon, we're going to look at the multiplicity. It's a quartet, which means it has 4 total lines, which if we remember our n+1 rule, n should equal 3. So on the adjacent carbon, we likely have 3 hydrogen atoms. So just like in the example table before, there is another possibility here in that we could have a CH2, a CH, and a CH2. If we just look at our table here, we know that we have another CH3 that we need to interpret here, so it's probably not too likely that we have this. If we had a lot more signals to interpret, we could keep that as a possibility here. But the other thing that really tips this off is the fact that we have this value up at 4, so it's likely that we have an oxygen, which we have in our molecular formula that we have to take care of, and that sort of inferred existence by the NMR into here. And so this is likely our partial structure that fits this NMR signal associated with it here. So let's look at our triplet. Our triplet again is 3 lines, and so again, if we look at our n+1 rule, n for this particular signal has to equal 2. So we can come up with a simple part structure for this as well, where we have our CH3 group that we're observing directly, and then adjacent to it is our CH2 group, and that's all we can infer directly from the analysis of this NMR signal, but these two fit with one another, and so they corroborate each other's existence. So let's look at this one here where we have 9 equivalent hydrogens. Well, we can't fit 9 hydrogens directly on a single carbon atom, so it's more likely that we have some sort of multiple of a group here. And it's most likely a multiple of a CH3 group. And so it's most likely that we have 3 equivalent CH3 groups to make this individual signal here. And one of the ways that you get this is by having a T-butyl group. That is, you have 3 methyl groups that are directly attached to a quaternary carbon. And these 3 methyl groups appear as the same on the NMR experiment because there's free rotation about this particular bond here, and so they can rotate around and they all look the same. So it's likely what we have here is 3 methyl groups attached to a carbon, and we're observing this signal here. So if we put our part structures together here, we have our ethyl group, and then we have our T-butyl group, and then we're missing something in this. So if we look at this, we have 4 carbons associated with this, 5, 6, and you can see that we needed a total of 7. We're also missing one of the oxygens. We can infer the existence of this oxygen here. So it's most likely that this is attached to a carbonyl, and we have our ester group here associated with this. If I can draw less sloppily a better structure for this in the stick figure on, that would be a proposed structure that would fit all of the NMR data associated with this particular signal. All right. So let's look at one that has a little bit more signals associated with it. And so I'll just pause here for a second to allow you to draw out your NMR table, so you can hit pause button so that you can follow along and maybe do this ahead of time before you watch the analysis that I'm going to do. All right, so hopefully you're coming back and you're ready with your NMR table to go through here. So again, let's start off by calculating our DU. So we have 5 carbons here, so we're going to do 2 times 5 plus 2. So we could have a total of 12 hydrogens associated with this, but in our actual signal we only have 10, and so we're missing 2 hydrogen atoms. And this is, of course, we could divide that by 2 to give our actual DU value of 1. All right. So let's go through here and let's fill in our chemical shift information. So we have a signal around 2.41. and that integrates for 2 hydrogens, and we're going to call that a triplet. And then we have a signal around 2.14, and that integrates for 3 hydrogens, and that is a singlet. And then we have something around 1.61, And that integrates for 2 hydrogens as well. And now it is a 1, 2, 3, 4, 5, 6. So it's a sextet. And then our final signal here at 0.95 is 3 hydrogens, and it is a triplet. All right, so let's look at some of the partial structures that we can have that will fit the data that we're observing. All right, so this signal at 2.41 corresponds to a CH2 group, right? That fits with the integral value that we're observing right here. And then we observe a triplet, and so it must be adjacent to another CH2 group. So that is where the coupling for the observed patterns come from. So that's one partial structure that fits with this particular signal. Another partial structure that could potentially fit with this, but I don't think is that likely, that should just be a CH, is if we had a CH2 group between 2 CH units. This would give a total of 2 neighbors as well, but since the only thing that we're observing here in our integral values looks to be like CH2 and CH3 groups, it's not as likely as this partial structure below. So then let's look at this signal at 2.14, and it's a singlet as well. So what we can see here is that we very simply have a CH3 group with no hydrogens on the adjacent carbon atom. All right, so that one's fairly simple to interpret. Now let's look at this sextet here, where we have a CH2 group based off of the integration values, and now we have to have 6 neighboring hydrogen atoms. So we can't have all of those 6 hydrogen atoms on the same carbon, because that would be greater than the possible valency associated with carbon, but we can have a CH2 on one side and a CH3 on the other. Sorry, we have to have 5 neighboring hydrogen atoms, not to explain our 6 lines that we see associated with this. So we see 6 lines, which again, we'll think about our n+1 rule, so n has to equal 5. Misspoke there. So the pattern that associates with this is an n-propyl group, where we're observing the central CH2 group associated with this, and then we have a CH2 on one side that gives 2 of the coupling values, and then a CH3 on the other side that gives 3 of the coupling values. All right, and we can begin to see that this is going to fit with our top structure, partial structure that we had for this signal here. And so let's look at our final signal here, where we have at 0.9, we have a CH3 group. And this CH3 group, based off of the integration value of 3, is split into a triplet, which means that it must have 2 neighboring hydrogens on the adjacent carbon, based off of our n+1 interpretation. And this fits with our partial structure that we laid out for our signal at 1.6 and 2.41. All right. So if we combine those 3 signals, what we end up with is very strong evidence for a propyl group. We don't know what's attached here. And then if we look at what we have on the other side is a CH3 group, but this CH3 group has to be attached to a carbon that doesn't have any adjacent, or doesn't have any hydrogen atoms on it. So what we can see here based off of our proton NMR spectrum is that we've accounted for 3, 5, 7, 10, all of our hydrogen atoms in our molecular formula. We've accounted for 4 of our carbon atoms, so we have another carbon in there. And then what we haven't accounted for is our oxygen. All right, so the only thing that we have remaining here is our carbon and our oxygen associated with this. And so we have this carbonyl unit that likely is the link here to put these 2 partial structures together. And so what we end up with here is 2-pentanone as our proposed structure that fits our NMR data. So I know this video is a little bit longer, but hopefully this shows you how to think about a lot of this proton NMR data. There's a lot of data here, and the major exercise that you want to take away from this is how do I manage this data, keep it all straight, and be able to work with this NMR system to make partial structures, to think about molecules in a very logical and systematic way. And then it becomes more of like a puzzle where you're figuring out here and you're being able to look at and determine an organic structure fairly quickly. All right, so good luck.